In this video, we will learn strategies for evaluating key physical properties of functional groups that we focused on recently. These include alcohols, ethers, and thiols. We covered these together because of the fact that they have some similarities in terms of what we expect as their predictable physical properties, as well as some differences. By the end of this segment, you should be comfortable comparing and contrasting physical properties of analogous alcohols, ethers, and thiols. As we think about these alcohols, ethers, and thiols, what are the physical properties that we'll focus on in this video? We will focus on both melting point and boiling point, which we will cover together because of the same type of intermolecular interactions that have to be disrupted in both cases. So we'll look at the melting point and how that will differ between these different types of compounds, the boiling point, and how those differ between these types of compounds. And those features are important because they dictate such things as the food properties of molecules that have these functional groups within them. They also help determine things like whether the molecules have an odor or not, because in order for a molecule to have an odor, it has to be present in the gaseous state so that it can be absorbed into our nasal passages and detected in that regard. We will also look at the important physical property of solubility in water, because in biological systems, these molecules are found within aqueous systems, and so that will be important in evaluating the biological properties of these compounds as well. So we'll look at water solubility as another key component here and compare and contrast these different types of functional groups that we will run into commonly within biological systems. Let's go ahead and get started and look at the physical properties here. To frame our discussion of melting points and boiling points, what I want to do is take a look in general at what determines the melting points and boiling points of substances. This will be more useful than initially looking at just the functional groups we're focusing on here, alcohols, ethers, and thiols, because the factors that we will discuss will be applicable toward all functional groups, including the ones that we'll learn about in later videos. And so these key tools here will allow us not just to rely on memorization to determine and compare boiling points between different substances, but instead will allow us to rely on our understanding of the concept, which will be much more broadly applicable and useful than simple rote memorization. So what determines melting point and boiling point? The bottom line factor that is going to determine melting point and boiling point is the strength of the intermolecular interactions between the molecules that are present within a container. So the strength of the intermolecular interactions is the main governor of melting point and boiling point. What do we mean when we talk about intermolecular interactions? It's kind of a big term there. We're going to break that down and unpack it a bit. Intermolecular interactions are referring to the interactions between different molecules. So it's interactions between different molecules within a container, not a molecule interacting with other atoms of the exact same molecule. So it's interactions between different molecules in a container. For example, if we had a bunch of ethanol in a container, ethanol is our 2-carbon chain with our OH group. The intermolecular interactions would refer to the interactions between, say, this alcohol molecule with this one, or this alcohol molecule with this one. So it's looking at how are the molecules engaging and interacting with others that are in the same container. What is the network that is going to cause those molecules to attract one another or to repel one another? The stronger the intermolecular interaction, the higher the melting point and boiling point. So if we increase the attraction between molecules, we will increase the boiling point or melting point, because in order to boil or melt a substance, you have to be able to disrupt the interaction that they are partaking in. So increased intermolecular interactions is going to increase the melting point, which I abbreviate as MP, and will also increase the boiling point, because these factors have to be, the intermolecular interactions have to be disrupted in order for a substance to melt or in order for a substance to boil. We have to disrupt the attraction that these structures have for one another. So what leads to an attraction of molecules to one another? Well, there are a variety of different factors, but one of the key ones that will be very, very strong is hydrogen bonding. So hydrogen bonding is an example of a very strong intermolecular interaction. So hydrogen bonding is a strong intermolecular interaction. And what is hydrogen bonding? May ring a bell from some of your general chemistry courses. Hydrogen bonding refers to the strong attraction between an electronegative atom, namely oxygen or nitrogen are typically the electronegative atoms that come into play in biological systems, of one molecule with the hydrogen of an OH or NH group of another. So strong intermolecular interaction from the electronegative atom, which I'll put as an E negative atom, and that's going to be an oxygen or a nitrogen of one molecule to the H, the hydrogen of an OH or NH group of another molecule. And so as we think about hydrogen bonding and the groups that we have looked at in the context of this chapter, alcohols, where we had a carbon chain or carbon ring directly bonded to an OH group, certainly can participate in hydrogen bonding, because the prerequisite for hydrogen bonding is that we have to have an OH or an NH group present in order for this to be able to act as both a hydrogen bond donor and a hydrogen bond acceptor. So what occurs in the context of alcohol molecules is we have this alcohol, then what will happen is that the alcohol interacts with other alcohol molecules, where I'll draw the other alcohol molecule like this, and the electronegative oxygen atom is strongly attracted to the positively polarized hydrogen atom there. And so these two atoms together form a very strong intermolecular interaction. Likewise, the hydrogen here forms a strong interaction to that oxygen, and so that creates hydrogen bonding there as well. Overall, the outcome of this is a very strong intermolecular interaction that is difficult to break. This is why water has a much higher boiling point than simple short-chain nonpolar molecules, such as, for example, gasoline volatilizes very well, very much better than water, because gasoline has a much weaker intermolecular interaction, because gasoline is just alkanes. Alkanes don't have the OH group or NH groups necessary for hydrogen bonding. And so that's going to greatly diminish the strength of their intermolecular interactions and make them boil and melt much more easily. So the stronger the intermolecular interactions, the stronger the hydrogen bonding, and hence the higher the melting point and the higher the boiling point. As a really dramatic example of this, if we were to look at the boiling point of ethanol, a 2-carbon alcohol molecule, we would find the boiling point of that would be approximately positive 80 degrees Celsius. On the other hand, ethane, where the only difference between ethanol and ethane is the lack of a hydroxy group, would instead have a boiling point around negative 90 degrees Celsius. So a very dramatic difference in the boiling points between these two substances. While hydrogen bonding is a very strong force in dictating melting point and boiling point, there are other factors that we need to consider and add to our list here. One of those key factors is the length of the longest carbon chain. So we're going to put length of chain onto our list. And the trend here is that the longer the chain, so the increase in the number of carbons in that chain, is going to increase the intermolecular interactions. And as we increase the intermolecular interactions, the trend is that the melting point and boiling point will go up. This chain length factor is not going to be as strong as hydrogen bonding in determining the intermolecular interactions. So when we're looking at intermolecular interactions and thinking about the impact on boiling point and melting point, hydrogen bonding is a first consideration. Second on the list would be the length of the carbon chain. The reason why a longer carbon chain leads to increased intermolecular interactions is because of van der Waals forces and other very relatively weak attractive forces between molecules in comparison to hydrogen bonding being a much stronger force. So if we have a carbon chain of 4 carbons versus a carbon chain of, we will say, 6 carbons here, there are more points for intermolecular weak interactions in the 6 carbon chain that has more atoms versus the 4 carbon chain, which has fewer atoms to pack together and engage in intermolecular interactions. Now, these intermolecular interactions that we see here do not involve hydrogen bonding. Hydrogen bonding is a much stronger force than what we observe here, and hence the impact of the length of the carbon chain on melting point and boiling point is usually secondary compared to the impact of hydrogen bonding. That is, unless you have a very, very long carbon chain that could lead to lots and lots and lots of intermolecular interactions. Now, along with the length of the carbon chain, another key factor that we need to consider is the branching of the carbon chain. And what we will observe for branching is that branching decreases the intermolecular interactions. If we increase the number of branches and the total number of carbons is the same, comparing apples to apples, so that both formulas have, we'll say C6H12, but one of the structures has more branches than the other, what we're going to find is the number of branches decreases the intermolecular interactions and hence allows the substance to boil and melt more easily. So taking a look at this, the reason why that's the case is hypothetically if we had 4 carbons in a chain versus a total of 4 carbons but arranged instead as a branch structure where we had instead a 3 carbon chain with a methyl branch coming off, both of these have 4 carbons and 10 hydrogens in total, so it is an apples to apples comparison, but the arrangement on the left allows for stronger intermolecular interaction or stronger packing of these substances because they are able to lay more smoothly and pack tightly, and that increases the intermolecular interactions, which means that the melting point and boiling point of these substances would be higher than the melting point and boiling point that we would expect over here due to the fact that there's less opportunity for intermolecular interactions and less strength of engagement between these two molecules due to the fact that they have those branches there kind of blocking or impeding or disrupting intermolecular interactions. So that is a third key consideration here. Hydrogen bonding being, I would say, the first thing to look at, length of the carbon chain second, and then if you're comparing two sets of molecules that have the same molecular formula, start looking at the branching of the chain, where more branching is going to correspond to a lower melting point and lower boiling point because it decreases the intermolecular interaction. So the bottom line here is that the melting points and boiling points are dictated by intermolecular interactions, where the key 3 things that we'll look at when gauging intermolecular interaction strength is hydrogen bonding, that is, does the molecule have an SH or an NH group to allow it to engage in hydrogen bonding? What is the length of the carbon chain as a secondary consideration? And then if we're looking at molecules that have the same formula, meaning the same number and types of atoms, which of those has more branches? More branches is going to correspond to reduced intermolecular interactions and thus a lower melting point and lower boiling point, meaning the substances will boil and melt more easily. Let's apply our knowledge toward an example problem where what we are asked to do is rank the boiling points of the 3 substances that I'm going to list the names of below, where 1 represents the lowest boiling point and 3 represents the highest boiling point. The three substances we will look at here are 1-pentane thiol, 1-pentanol, and we will also look at pentane. Ranking those in order from the expected lowest boiling point to the highest boiling point, we think about these intermolecular interactions, with hydrogen bonding being first and foremost as we look at these. We have a thiol group, an alcohol group, and an alkane group. The only one of those three that's capable of hydrogen bonding is going to be our alcohol. And so therefore, I'm going to rank that as having the highest boiling point because of hydrogen bonding. If you were asked to explain why you made that assignment, it is because this is the only one of the three that's able to hydrogen bond. Hydrogen bonding makes the intermolecular interactions very strong. Second on the list of pentane, thiol, and pentane. Now this one might be a little bit more confusing because we haven't talked specifically about thiols in this discussion yet relative to alkanes. That does bring up an additional point that when we are looking at boiling points, generally the more polar the molecule, the higher the boiling point as well. And so comparing thiols to pentane, thiols with an SH group where the sulfur is somewhat electronegative. It's not as electronegative as oxygen, hence it's not able to technically hydrogen bond, but it is in the same column of the periodic table as oxygen and has some polarization of the carbon-sulfur bond. That polarity will increase the boiling point of the structure as well compared to an alkane. So we're going to put that as number 2 and the alkane molecule as number 1, the lowest boiling point of these three. Let's take a look at another example here. So in the case of this example, we're going to rank the boiling points again for 3 substances. So in our lineup now, we have 2-propanol, 1-hexanol, and 3-methyl-2-pentanol. If we draw out those structures to get a full feel for what they look like, 2-propanol, 3-carbon chain with a hydroxy group at carbon 2, 1-hexanol, 6-carbon chain with the hydroxy group at carbon number 1, and 3-methyl-2-pentanol. Let's draw out a 5-carbon chain here. And at position number 3 of the chain, we put our methyl group. At position 2, we put our hydroxy group to give the complete structure of that. Now, assessing these based on our understanding of intermolecular interactions, all 3 of them are very proficient at hydrogen bonding because all 3 have 1 hydroxy group apiece. So they're all pretty equivalent in terms of how well they're able to hydrogen bond. So we have to look deeper at additional factors, where the additional factors are length of the carbon chain first, followed by the extent of branching of the carbon chain, where the shorter the carbon chain, the lower the intermolecular interactions, and hence the lower the boiling point. So in the case of 2-propanol, that has a shorter carbon chain than hexanol or 3-methyl-2-pentanol with far fewer carbons here. That 2-propanol is going to have the lowest boiling point of all of these. And so I'm going to list that as number 1 because we're asked to list the lowest boiling point as number 1. Second lowest, we compare then 1-hexanol to 3-methyl-2-pentanol. Both of these have 6 carbons in total, but in the case of 1-hexanol has fewer branches and hence a longer carbon chain, and as a result, it's going to have stronger intermolecular interactions and a higher boiling point as a result of those stronger intermolecular interactions. So I'm going to put that as 3, meaning the highest boiling point, and our branched structure as number 2 here, because branching results in a reduction of the intermolecular interactions. We talk about water solubility in tandem to discussing melting point and boiling point because water solubility is going to also rely upon intermolecular interactions, where the stronger the intermolecular interaction between water and the molecule of interest, such as a thiol, alcohol, or ether, the more water soluble the structure will be. And the general term that is used to describe this is like dissolves like. Substances that are similar in the types of intermolecular interactions that they engage in will be soluble in one another. Water is, of course, a very polar solvent due to the fact that it has the electronegative oxygen atom bonded to a much less electronegative hydrogen, making the bond between oxygen and hydrogen very polarized due to that electronegativity difference. Water is also capable of hydrogen bonding. And therefore, substances that are soluble in water are going to be, ideally, as polar as possible and capable of hydrogen bonding. So in the context of water solubility, what's going to favor water solubility as we think about organic functional groups is, with regard to polarity, the shorter the carbon chain, the more polar the molecule will be, because carbon chains are full of carbons and hydrogens with little electronegativity difference between those and hence very polar compounds. So decreasing the length of the carbon chain will increase the water solubility. Thinking about hydrogen bonding groups are NH and OH out of organic molecules. And so NH and OH groups will result in an increase in water solubility relative to other groups that are present within organic structures. So as the carbon chain length increases, the water solubility of alcohols and other molecules will decrease, because there's essentially a tug of war going on where one part of the molecule, that is the alcohol group, will favor water solubility. On the other hand, the other part of the molecule, this alkyl chain, disfavors solubility because it is very unlike the alcohol group, very unlike the water molecule. So this will disfavor solubility. So as the length of this chain increases, the water solubility as a consequence will decrease. With these principles in order about the relationship between the carbon chain length and hydrogen bonding with water solubility, we can apply this toward comparison of the water solubility of a thiol versus an alcohol. So for example, if we were to compare the water solubility of one pentane thiol relative to one pentanol, and by the way, we could have put the alcohol group at any position along that chain or any position along the thiol, and the trend here would be the same, which is that due to the fact that alcohols have that group that's able to hydrogen bond, the water solubility is going to be much greater for the alcohol than it is for the thiol, because the thiol group is not polarized enough between the S and the H to effectively hydrogen bond. And that hydrogen bonding is going to increase the like properties of the alcohol with water and hence lead to the alcohol being far more soluble than the thiol molecule. Likewise, we could also compare and contrast ethers. So we could do, for example, diethyl ether. Diethyl ether would have a 2-carbon chain here, oxygen, and then a 2-carbon chain over here. This is not a bat or other bird flying in. It is an organic molecule. And if we compare that to, we'll say 2-butanol, or butan-2-ol, so 4-carbon chain, hydroxy group there, carbon number 2, we would predict correctly that the 2-butanol would have a higher water solubility because of the fact that it is able to hydrogen bond, whereas diethyl ether is unable to hydrogen bond. For that same reason, diethyl ether would also have a lower boiling point or melting point because it's not able to engage in that strong intermolecular interaction.